One city, one river, two islands, and seven bridges. Here's the bet. Go for a walk. Start wherever you like, finish wherever you like. One single rule. Cross each of the seven bridges exactly once. None twice, none skipped. Sounds like a puzzle for a rainy Sunday afternoon. The citizens of Königsberg tried it for decades. Sunday after Sunday, route after route, with the confidence of people who know their own city. Nobody ever managed it, and nobody could say why not. There was no point where it obviously broke down, it just never quite worked out. And here's the number that tips the whole thing over. Those seven bridges can be walked in 5,040 different orders, 5,040 attempts, and all of them fail. Not from bad luck, because the city itself forbids it, and that can be proven. On half a page by a man who first refused to look at it. This bet is the origin of two entire fields of mathematics. Graph theory was born from it, the language in which road networks, power grids, social networks, and the internet are described today. And alongside it, topology, the mathematics of shapes you're allowed to bend. Both of them, out of a Sunday stroll. And it all traces back to a single paper, written by a man who first considered the problem unmathematical and couldn't be bothered with it. And the trick he finally settles it with is so simple you could explain it to someone at the kitchen table tonight, without a single formula. We'll retrace the path he took, from "that isn't really maths" to the sentence that settled the matter for all time. Let's start with the city. Königsberg, 18th century, capital of East Prussia. The river Pregel runs straight through it, and it cuts the city into four pieces. There's the north bank, there's the south bank. Between them lies an island, the Kneiphof, with the cathedral, the heart of the city. And further downstream, where the two arms rejoin, sits a fourth piece of land, the Lomsee. Four pieces then, separated by water. To get from any one to another, you must cross a bridge. That is all the geography you need. 7 bridges connect these 4 parts. They had names out of a fairy tale: Merchant's Bridge, Blacksmith's Bridge, Honey Bridge, Green Bridge, Giblet's Bridge, High Bridge, Wooden Bridge. 5 of them lead to the Kneiphof. The island is the bottleneck. Half the network hangs off it. The remaining 2 link the other banks to each other. And that's the entire problem statement. No hidden ferries, no tunnels, no swimming. The original is explicit. Bridges only. Remember that 5. In a moment it becomes the deciding number. Let's try it. Start on the north bank, cross to the island, onto the south, back to the island over the next bridge. And now 3 bridges are left, but we're standing in the wrong place. One of them is only reachable if we reuse a bridge we've already crossed. So back. Different start, different order. 6 bridges we manage almost every time, 6 out of 7, and every time exactly 1 is left over, unreachable. Sometimes it's the Honey Bridge, sometimes the High Bridge, depending on where you started, but 1 always remains. And if you're thinking, fine, I'll start on the island then, tried that too. Also 6. And that feeling, I was so close, is the trap. It suggests the fault is yours, the order, your cleverness. It's none of those, it's the city. And to see that, somebody had to stop walking and start thinking. In 1736, the mayor of Danzig, Karl Leonhard Gottlieb Euler, writes a letter. Addressee, Leonhard Euler, then in St. Petersburg, the most productive mathematician who ever lived. Euler politely asks for the solution, and for a proof. He suspects something new is hiding in there. A calculus of position, as he calls it, and he tells Euler this would be an outstanding example of it, worthy of his great genius. You may read that as flattery, it only half works. Euler replies on the 3rd of April, and his reply is, for a man who would later rewrite half of mathematics, remarkably unimpressed. This type of solution, he writes, bears little relationship to mathematics. It rests on reason alone, discovering it requires no mathematical principle whatsoever. Translation, nice riddle, not my department. It's hard to blame him. In 1736, mathematics meant numbers, magnitudes, curves, motion. A riddle without a single number in it looked like a pastime. And then he does what geniuses tend to do once they've declared something unimportant. He thinks about it anyway. Probably because what drew him wasn't the riddle, but the question behind it. What kind of mathematics would this even be, if it were any? That same year, he presents the solution to the Petersburg Academy. The paper is titled, Solution of a Problem Relating to the Geometry of Position. The geometry of position, not of size. That one word holds the entire invention. Because to crack the bet, Euler first has to do something unheard of at the time. He has to throw the city away. Not the bridges, the city. Look at the map and ask yourself, what part of this do you actually need to settle the bet? The length of the bridges? Irrelevant. You have to cross, whether it's 20 meters or 200. The shape of the island, the streets on it, exactly where the cathedral stands? Irrelevant. As long as you're on the same piece of land, you can walk anywhere on it without using a bridge. Compass directions? The bend of the river? Irrelevant. Irrelevant. Whether the Pregel runs fast or sluggish, whether the island is oval or angular, none of it can settle the bet. Exactly one thing survives. which piece of land connects to which, over which bridge. So Euler deletes everything else. Every piece of land shrinks to a dot. Every bridge becomes a line between two dots. 4 dots, 7 lines, there's your city. The picture now looks like a child drew it, and it still contains everything the question needs, and nothing it doesn't. Pause here, because this is the real moment. What just happened looks like a simplification. It is in fact an invention. Euler has just built for the first time an object made of nothing but relationships, things and their connections, and nothing else. No more distances, no shapes, no names, only connected or not connected. Today that object is called a graph, and today it is everywhere. A metro map is a graph, your circle of friends is a graph, the internet is a graph, molecules are graphs, power grids too. Every time your navigation app plans a route, this idea's great-granddaughter is running inside it. Every time a search engine decides which page matters, it is counting connections in a graph, and the bet, on the graph it's settled in about a minute. Which is the strange thing about abstraction, it feels like you're losing information. What actually happens is that the answer stops hiding. Here comes the proof, and it needs not one single formula. Think of any dot in the middle of your walk, not the start, not the finish. What happens there? You arrive across one bridge and you leave across another. In, out, 2 bridges per visit. Come back later, 2 more. And again, 2 more. So the bridges at an in-between dot always get used up in pairs, always 2 at a time. And that forces something. At every dot that isn't the start or the finish, the number of bridges must be even. Otherwise, one lone bridge is left over that you can never serve. You arrive and you're stuck, or you'd have to fly in. Only start and finish are allowed to break rank. At the start, you leave once without having arrived. At the finish, you arrive once without leaving again. Those 2 exceptions are the entire allowance you get. 2, not 3, not 4. That gives us a rule that holds for every walk on every network in the world. Dots with an odd number of bridges can only be the start or the finish. And since a walk has exactly 1 start and exactly 1 finish, there may be asterisk at most 2 such dots. Now let's count in Königsberg. The Kniehof, the island in the middle, 5 bridges, odd. The north bank, 3, odd. The south bank, 3, odd. The fourth piece of land, 3, odd. 4 dots, all 4 odd. At most 2 are allowed. And with that, the bet is settled, not for today, not for you, but for every person in all time. There is no route, there can't be one. Those 5,040 attempts were never a competition, they were an appointment with failure. And notice what this proof does not do. It tries nothing out. It never looks at a single route. It counts 4 numbers and it's finished, which is why it also works on networks with millions of edges, where trying things out would be hopeless. And here's the beautiful part. The proof doesn't only tell you that asterisk it can't be done. It tells you how to spot it instantly in any other network, count the odd corners. Now look at what became of this Sunday stroll. Euler's criterion answers not just Königsberg but any network. 0 odd corners means you even return to where you started. A perfect round trip. Exactly 2 means it works, but you end up somewhere else. More than 2 means impossible. 3 cases, that's all. No exceptions, no fine print, no matter how big or tangled the network gets. Anyone planning the route of a garbage truck today, or a snowplow, or a street sweeper, is asking exactly this question. Every street once, none twice, no empty miles. And when a network has too many odd corners, and real cities almost always do, the same theory tells you which stretches are cheapest to drive twice, so it works out anyway. Every saved double run is diesel, time and money. How do I cross all 7 bridges became how does a city clear its snow at the lowest cost? The Sunday walkers of Königsberg were, without knowing it, beta testing a logistics algorithm. And Euler himself? With the same paper he pushed open a second door. Geometry of position, the mathematics of what stays the same when you bend and stretch everything. That's topology. Without it, there'd be no modern physics, no understanding of knots, surfaces, spaces, no way to say what a hole even is. Both of them, graph theory and topology, begin in the same short paper about a riddle its own author considered hardly mathematical. Sometimes the most important question isn't the hardest one, it's the one where somebody is first to notice how much you're allowed to leave out. The bet from the beginning stays unlost and unwon. Across the 7 bridges of Königsberg, there is no walk that takes each exactly once. 5,040 attempts, 5,040 dead ends, and a proof that fits on half a page. But the prize was never the route. It was the moment when somebody looked at an entire city and decided to forget almost all of it. Streets, lengths, shapes, names, until only dots and lines were left. Only in that poverty did the answer become visible. As long as the city stayed a city, the question was unanswerable. Once it became 4 dots, it was easy. Next time you're facing a problem that looks hopelessly tangled, that may be the single most useful question available. What am I allowed to leave out? Königsberg answered it with 2 entire disciplines. Still here? Then you get the thing about the 8th line. You may have spotted it, right at the beginning, dashed, with a question mark. I never explained it. Here it is. Königsberg is called Kaliningrad today, and the city did not keep its 7 bridges. 2 were bombed in 1944. 2 more vanished in the 70s beneath an elevated highway, swallowed by the concrete of Leninsky Prospect. 5 are left, and now count the odd corners of this new network with me. Island, 3. North Bank, 2. South Bank, 2. Fourth Land, 3. 2 odd corners, exactly 2. 0 or 2 are allowed, and 2 is allowed. The walk Euler declared impossible is possible today, not because anyone disproved the mathematics, but because bombs and a concrete pillar changed the graph. The theorem still holds. It's the city that adapted to it. If you ever make it to Kaliningrad, start on the island, and then walk. Somewhere out there is a Sunday afternoon that Königsberg never got to have.